Why does the ground suddenly decide to move? Not gradually, not politely, but all at once. Imagine you're sitting at a table. A glass of water is perfectly still. The walls are doing their normal job of remaining walls. Then the floor shifts beneath you. The glass rattles, the room creaks, and for a few seconds, the ground stops behaving like the one thing you thought you could trust. That's what makes earthquakes so strange. The Earth looks stable because we experience it at human speed. Roads stay where we leave them. Mountains seem permanent. Buildings are designed around the fairly reasonable assumption that the ground won't abruptly wander off during lunch. But beneath all of that, the planet is moving. Constantly. So why don't we feel earthquakes constantly? The usual answer is tectonic plates. Earth's outer shell is divided into enormous slabs. Those slabs move slowly. Sometimes they collide. Sometimes they pull apart. Sometimes they scrape past each other. Eventually, one slips. Earthquake. That explanation is correct, but it isn't the real answer. Plate movement explains where the pressure comes from. It doesn't explain why the ground stays still for years, decades, or centuries before suddenly lurching. And it doesn't explain every earthquake. Some begin beneath volcanoes. Some begin when underground spaces collapse. So the real mystery isn't why Earth moves. It's why hidden movement suddenly becomes shaky. To understand that, we have to begin with something that sounds impossible. The ground can be moving and stuck at the same time. Along a fault, two masses of rock may be pushed past each other by forces moving through the crust. But the fault surface isn't smooth. It's rough, fractured, crushed, and full of irregular edges. Parts of it catch. Friction grips the rock. The fault remains locked. Meanwhile, the plate behind it keeps moving. Very slowly. Usually at speeds measured in centimeters per year. That sounds harmless. Hair grows faster, right? But unlike hair, tectonic plates are moving sections of continents. The locked fault doesn't stop the force. It delays the movement. So the surrounding rock begins to deform. It bends slightly, compresses, stretches, stores energy. The fault stays stuck, but the pressure keeps building. Eventually, part of the fault can no longer hold, and it slips. The rupture may begin in one small underground patch. That movement changes the forces on the rock beside it. The neighboring patch may slip too. Then the next one. Then the next one. And the rupture spreads along the fault. A fault may have been loading for centuries, but the rupture can race through it in seconds. That sudden movement sends energy outward through the Earth as seismic waves. Those waves are the shaking. So an earthquake isn't the Earth beginning to move. It's movement that has been delayed finally breaking loose. The first waves to arrive are called P waves. They squeeze and stretch rock in the same direction they're traveling. They move quickly, which is why instruments can detect them before the strongest shaking arrives. Then come S waves. These move the ground from side to side, or up and down, across the direction they're traveling. Near the surface, other waves can create rolling, swaying, or violent sideways motion. The ground isn't shaking as one solid piece. Different waves move through different materials at different speeds, arriving from different directions. That explains why two places the same distance from an earthquake can experience very different damage. One neighborhood may shake hard and remain mostly intact. Another may suffer badly. The difference may be the ground beneath them. Hard rock transmits shaking differently from loose sediment. Soft soil can amplify motion. Sediment-filled basins can trap waves and keep the shaking going longer. Even after an earthquake begins, the geology under your feet gets a vote. A very loud vote.
Yes! Yes!
The underground point where the rupture begins is called the hypocenter.
The epicenter is the point on the surface directly above it. That means the epicenter isn't where the earthquake began. It's some map marker. And it isn't always where the strongest shaking occurs. A large earthquake may rupture a long stretch of fault, so reducing the whole event to one neat dot is convenient but slightly deceptive. The earthquake is not living inside the dot. Now the simple explanation starts to crack, though. Tectonic faults aren't the only way to produce seismic shaking.
There are three broad natural types of earthquakes. The first is tectonic. These happen when stress builds along faults and rock suddenly slips. They're the most common type.
Okay.
They also produce most of the largest earthquakes. But beneath volcanoes, the mechanism can be different. Magma moving through the crust can force open cracks. It can increase pressure. It can push against surrounding rock. Volcanic gases and fluids can also move through fractures and change pressure inside them. This can create swarms of small earthquakes beneath or around a volcano. Sometimes those earthquakes reveal that magma is moving. Sometimes they happen without an eruption following. A volcano can become seismically noisy without making any promises. The third type is a collapse earthquake. These happen when an underground space suddenly gives way. A cave roof may fall, a mine tunnel may collapse, part of the ground may drop into an empty chamber below. The collapse releases energy and produces seismic waves. These events are usually smaller and more localized than major tectonic earthquakes, but the basic pattern is similar. Something underground resists movement. That resistance fails, something moves suddenly. Energy travels outward, the ground shakes. That same pattern helps explain why some human activities can trigger earthquakes. Injecting fluid deep underground can raise pressure inside existing faults. Mining can remove support from underground rock. Reservoirs can add weight and allow water to seep into fractures. Geothermal projects can change underground pressure. In many cases, humans aren't creating a new fault. They're changing the conditions around one that is already stressed. Fluid pressure can reduce the grip holding it shut.
The fault slips sooner than it otherwise might have. That doesn't mean every earthquake near human activity was caused by it. Fault systems are complicated, and proving cause requires evidence. But induced earthquakes are real. Then there are aftershocks. When a major fault slips, the surrounding crust has to adjust. Stress is removed from some areas and transferred to others. Nearby sections may now be closer to failure. Those later earthquakes are called aftershocks. They usually become less frequent over time, but not according to a tidy schedule. And a smaller earthquake that happens before a larger one is only called a foreshock afterward. Before the larger earthquake, it's just an earthquake. There is no underground label saying preview. That leads to one of the biggest unanswered questions in earthquake science. Can we predict exactly when a fault will rupture? Not reliably.
Sorry, mate.
Scientists can identify dangerous faults. They can measure how regions are deforming. They can study past earthquakes, map hazards, and estimate probabilities over years or decades. But they can't yet point to a fault and confidently say a magnitude 7 earthquake will happen there next Tuesday afternoon. Faults aren't simple timers. They contain different rock types, uneven surfaces, fluids, branches, old fractures, creeping sections, and locked sections. They also interact with nearby faults. Much of the important action happens miles underground, where direct observation is problematically difficult. Scientists understand the overall process very well, but understanding the machinery isn't the same as knowing the exact second one hidden part will fail. Researchers have studied unusual ground movement, changes in fluids, small earthquake patterns, electrical signals, and reports of strange animal behavior. No single warning sign has proven dependable enough to predict earthquakes consistently. Animals may sometimes notice the earliest weak waves before humans do, though. That means they're reacting quickly,
Watch out!
not forecasting the future. Earthquake early warning systems work in a similar way. They don't predict an earthquake before it starts. They detect the first waves after rupture has already begun, then send alerts faster than the more damaging waves can travel. Depending on distance, that may provide a few seconds or longer. Not enough time to leave town. Enough time to stop trains, pause machinery, or move away from something likely to fall.
And now we reach the strangest part. When an earthquake begins, it may not be obvious how large it will become. A small earthquake and a large earthquake can both begin with failure on one patch of a fault. The difference is whether the rupture stops. A small patch slips and stalls, or it keeps going. One section triggers the next. The rupture grows. More fault area moves. More energy is released. A massive earthquake may begin as a local failure that simply refuses to stop. That doesn't mean large earthquakes are random. They require faults large enough, stress high enough, and conditions that allow the rupture to spread. But whether the first seconds reveal the final size is still an active area of research. The answer isn't fully settled. Deep earthquakes create another puzzle. Some happen hundreds of miles beneath the surface, where heat and pressure should make rock behave less like brittle stone and more like slowly deforming material. Yet earthquakes still happen there. Scientists have several possible explanations involving mineral changes, released fluids, and sudden instability inside descending slabs. The exact mechanism is still being investigated. So why do earthquakes happen? Because something underground is forced, pressurized, or supported until it can no longer remain as it was. In tectonic earthquakes, faults slip. In volcanic earthquakes, magma, gases, and fluids disturb the surrounding rock. In collapse earthquakes, underground support suddenly fails. Different causes, same abrupt result. The Earth spends most of its time hiding motion from us. Plates creep, rock bends, pressure builds, cracks weaken. Everything appears still because the process is slow and buried. Then, for a few seconds, the hidden motion reaches the surface. An earthquake isn't the moment the Earth starts moving. It's the moment the Earth can no longer hide that it already was. If you have a question rattling around your brain that you want answered, drop it in the comments, and maybe we will give it a shake. Until then, you can scratch it with our last video. Why do mosquito bites itch?
Hey, look, a new subscriber.